All right, now our next theorem is a generalization of the LYM inequality proved by Bollobás in 1965. Okay, this is when he was very, very young. So we have two sets of two families of sets. A1 up to AM and B1, B2 up to BM be subsets of 1 up to n such that two conditions hold. So AI intersection BI is non-empty. Empty. So they are disjoint for all I. And secondly, AI intersection BJ is non-empty for all I different from J. Then we want to prove the following inequality. From 1 up to n, 1 over AI plus BI, choose AI is the most one. Right. So why is this interesting? So let me add a remark. Why does it imply LYM inequality? So if F is an antichain, then take BI to be the complement. Then it satisfies 1 and 2, right? If you take a complement, then intersection of AI and BI is going to be empty. And since AI is never a subset of AJ, so that means BJ intersect AI. And then what you get is this LYM inequality, right? And choose AI is at most 1, right? So this Bollobás' theorem extend LYM inequality. And the proof is really cute. Again, we use permutations, right? For each I, let Pi be the set of all permutations of 1 up to n such that what's going to happen? So the elements of AI, all elements of AI occur before every element of BI. So that's the definition of PI. So, right, so AIs are here and BIs are here, right? So that's instance of PI, permutations in PI. And then I know that the number of them is, well, first of all, I choose the positions for these places. So n choose AI plus BI. And then for each position, then I have AI factorial ways to fill the first AI many slots. And then BI factorial ways to build the remaining BI entries. And then for remaining entries, I can just permute the remaining numbers. So that's the size of PI. Now, if I look at the intersection of PI and PJ, right? So in PI, all the AI occurs before BI. So this is going to be PI and then PJ. In PJ, all the AJs occur, or the all the AJs occur, or the BJs, right? So these are the PI and these are the BJ, AJ, AI, right? So if PI intersection PJ has some common permutation, what's going to happen? right? So in order to have a common thing, but I know that AI must intersect with BJ, so there's an element here, the common element, and there's also common element between AJ and BI, but then the ordering is not consistent, right? So there's an element which appears in AI and BJ, there's an element which appears in AJ and BI. If the previous element is smaller, then it has to occur earlier, but in the next permutation it doesn't occur earlier, right? So the PI intersection PJ is empty. So that means the sum of the permutations, sum of the number of permutations is less than n factorial. Now it's easy to compute this formula, so it's n choose AI plus BI times AI factorial, BI factorial, n minus AI minus BI factorial is less than or equal to n factorial, and let's arrange them. Then what do we get? I can divide n factorial on both sides, so this is AI plus BI factorial over AI factorial BI factorial and 1. This is less than or equal to 1, so this is sum of 1 over AI plus BI, which is AI is less than or equal to 1. All right, so that's the proof. That's a really cute proof. All right, there's a uniform version. So uniform version is what? So let's say A1, A2, AM are the, and B1, B2, BM are subsets of 1 up to n, where AI has size R, BI has size S for all AI. Then if AI intersection BI is empty and AI intersection BJ is non-empty for all I different from J, then the number of them is at most R plus S choose R. You can easily see why this is true, because once you apply this inequality and all AIs are R, all BIs are S, so this is what you get. And again, now you can see why this is best possible, because you can take the, so for instance, take numbers from 1 up to R plus S and let AI be the subset of size R and BI be the complement, then it's obviously it satisfies 1 and 2 and it's equal, right? So that's why it's tight. So later we will see the generalization of this version, where we're gonna relax this condition. Instead of I equal to J, not equal to J, we will replace it by a weaker condition, saying namely I less than equal to J. For this version, we don't have any combinatorial proof. The only proof known is to use some technique from algebra. So we're going to do that. But before doing that, we'll discuss an application of this two families theorem, which is actually motivation for Bollobás. Why he studied this, why he proved this lemma, is because he wanted to prove something on graphs. All right, and then